Okay, so we are on our last section of finding volumes of solids, and also this is the last new thing that we have to learn in AP Calculus. So today what we're talking about is finding the volumes of solids using cross sections. So I'm using this applet here to visualize what that means. So let's say you have a base area, in this case between the red function and the blue function. So each of these is kind of a representative rectangle of the base of this solid. So you can see in the three-dimensional figure that it's going to become the base. That's why it's flat. And then what we're going to do is we are going to use squares. Okay. Now what I mean by the base of a solid is you can see that you have these squares, and when you have enough of these squares, it creates a solid figure where every slice, kind of like a loaf of bread, every slice is a certain shape. And in this case, every slice is a square. Now you'll notice that some of the squares, like on the end here, are very small, and then in the middle, the squares are larger. And that's because the one thing you know about squares is that the sides are equal. So if the base is large, so like for example, when you're in the middle here, if your base is large, then your height will also be proportionally as large. Whereas if you are near the edge here, your base is smaller, and so your height is smaller. So what we're going to be doing is adding up a bunch of these squares to make this figure where the base is on the graph between this function and this blue function here. Okay, so that's in squares. Let's do the same thing but with triangles. So these are all equilateral triangles, meaning that wherever you are in terms of the base in between the red and the blue graph, so this side length is going to be equal to the other two side lengths here. So again, as you're at the edges here where the space in between is really small, that means that triangle is also going to be proportionally smaller. Whereas in the middle here where the base is larger, the equilateral triangles are larger as well. And then lastly, what would it look like if everything was a semicircle? So all of these slices are half circles. And so all of these figures look different depending on what the cross-section is. So when I say cross-section, what I mean is like, what is the slice? So the slice of each cross-section could be semicircles, it could be full circles, could be squares, equilateral triangles, it could be all sorts of other things. These are just 3 examples of what the shapes could be, okay? So I'm gonna jump right into an example in your notes. Okay, so in this example that's in your notes, we're gonna follow these steps that are outlined on the previous page. And it's, yeah, I'm just going to go ahead and get started. Okay, so the solid lies between the curves the square root of 1 minus x squared, y equals negative 1/2 x minus 1/2, and x equals 1. Find the volume of the solid created where the cross sections are full circles with diameter in the xy plane perpendicular to the x-axis. Okay, so first thing we're going to do is draw a graph of the base equation. So I'm going to graph x equals 1. So I'm going to say this is x equals 1. The square root of 1 minus x squared. So if you plug in 0, you get 1. If you plug in 1, you get 0. If you plug in negative 1, you get 0. This is a half circle, semicircle. And then the graph negative 1/2 x minus 1/2. So if I'm at negative 1/2, so let's say this is negative 1. So this is like negative 1/2. And then a slope of negative 1/2, so it's going to look like this. Okay. So I'm talking about this region right here. Actually, I don't want to fill it in. And on this region, so you have to recall that this is a 2-dimensional base. Now, if I were turning this into 3 dimensions, so I have some base that looks like this almost. And then imagine that you have full circles with the diameter. Oh, that's not a good circle. Okay, like that. So each slice is a circle with the diameter in this plane. So I'm trying to like draw a three-dimensional figure for you where you can see this a little bit better. So like here's a diameter, and you have a circle like right here. So something that looks kind of like that. And then as you have more and more circles, so we'll have like a small circle over here, a really small circle here, and it'll kind of create this, this three-dimensional figure, so something like that. So I'm not super concerned with you drawing the three-dimensional figure in this case. I really just want the graph of the base equation to be clear. And then the diameter is perpendicular to the x-axis, which means perpendicular to the x-axis is going to look like this. So imagine that that is the diameter of a circle, and the circle's like half of it's going to be above and half of it's kind of below. So that's going to be like one base of a typical slice, and each slice is a circle. Okay, then 2, find the equation of one cross-section in terms of the base. So let's look at one cross-section. It's a circle, with the diameter is the base, and we're going to write it in terms of B, which is why if you're in my class, I asked you to do the areas in terms of B part of your notes, where you find the areas of all different shapes in terms of the base, because we're going to have to do that for each of these problems. So the area of a circle is pi r squared. It's a full circle. Now the base is the diameter, so I need to find the radius in terms of the base. So the radius is obviously half of the base. So I get area equals pi times b over 2 squared. Go ahead and simplify as you go. So that's pi b squared over 4. So each slice has an area of pi b squared over 4. So that's the area of a slice. And if you think about the volume of one slice, the volume of a slice is the area times the thickness. So the volume of one slice is the area times the thickness of that slice. And of course, we're going to want an infinite number of these slices in order to get an accurate estimation of the volume. So that means the thickness is going to be very, very, very small. It's going to be approaching 0. In this case, it's dx, because if it was, let's say it was like really thick here, okay, then that would mean it would be like this x value minus this x value in order to get the thickness. So that's dx as that thickness approaches 0. So as we have a really thin slice, the thickness of that slice will be dx. Okay, so then we are using an integral to represent adding up all of the cross-sections, including the thickness of each cross-section. So I'm not going to even do bounds at this point. I'm just going to say, okay, I'm adding up all of these slices. Now the area of one slice is pi b squared over 4, and the thickness, as I just said, is dx. And so what that tells me is I'm going to be, because the thickness is dx, my bounds will be in terms of x, and I need to write my base in terms of x. So everything is going to be in terms of x here. Okay, then we want to, step 4, substitute the base equation into the integral. So that's going to be the integral from, and now because I'm in terms of x, I can look at my bounds. So I have a bound here of -1 and a bound here of +1, so -1 to 1 of, and the base itself is this region right here. If I were to draw in all of the bases, it would be like all filled in, right? So all of those bases are going to be the upper function minus the lower function. In other words, it's the area of the figure that you see. So that's going to be the pi over 4. And then b is going to be the area in between the curves. So that's the square root of 1 minus x squared minus the line -1/2 x. I can clean this up later. So that's going to be what my base is. So this is the b part. That is the base of the figure, and what you see in this graph is the base of the three-dimensional figure. Sorry, my computer keeps freaking out. Okay, times dx, which is the thickness. So you don't need to try to simplify this anymore. You cannot distribute the squared What you can do is if you want to, you can take out like the pi over 4 part and then like distribute the negative so that you have plus 1/2 x plus 1/2. But that still needs to be in parentheses with the squared on the outside because it was the whole base squared. And then the thickness is dx. And then you can just plug it into a calculator to calculate what the volume actually is. So let's do another one. So we still have the same solid, so it's still going to be, I'm just going to do a quick sketch right here. It's still going to be like this. Okay, but in this case, the cross sections are triangles with bases perpendicular to the x-axis, whose heights are 3 times the base. So it's not an isosceles or an equilateral triangle. It's a triangle whose height is 3 times the base. So that means wherever your base is, so let's say you have a base here, that's the base of that triangle. That means the height of the triangle is going to be like 3 times as tall. So just imagine that you have like a bunch of these triangles kind of coming up from that base. Again, very hard to draw this in 3 dimensions. So then we need to find the equation of one cross section in terms of the base. So I have a triangle. Its height is 3 times the base. So if the base is here, and remember, always draw your base as horizontal. So then the height is going to be 3b. So the area of one slice is going to be 1/2 base times height. So that's 3 over 2b squared is the area of one slice. And the volume of the slice is the area times the thickness. And the thickness, again, is going to be dx. So use an integral to represent adding up all of the cross sections. So that's going to be the integral of 3/2 b squared, adding up all of those slices times the thickness of each slice. And because it's dx, I need the base to be in terms of x, and the bounds also need to be in terms of x. We already found the bounds before, -1 to 1 of 3/2. And then your base, again, if you think about all of these bases, all of them have a length that is in between the upper function and the lower function. So the base is going to be, again, the square root of 1 minus x squared minus -1/2 x minus 1/2. So that's the base. This whole thing is the base, upper minus lower, squared, and then dx. So that's your integral when you have slices that are triangles where the height is 3 times the base. Okay, and then lastly, again, same figure. Okay, in this case, the cross sections are squares with diagonals in the xy plane perpendicular to the y-axis. So what that means is I'm going in a different direction now. So like this would be one slice here, this would be one slice here, perpendicular to the y-axis. This will be another slice, and that's the diagonal of a square. So think about, you have I'll just draw the square over here. So you have a square, all the sides are the same, but the diagonal is the base, okay? So each of these bases, think about like in the middle of a square. So it's like half of the square is gonna be above, and then half of the square would be below. So if you think about all your slices with like a triangle above and a triangle below, and that's gonna create your 3-dimensional figure here. So, sorry, I just want to clean this up a little bit. Okay. So the area of one square is, let's call this side like C, okay? Well, the area of a square is C squared, right? It's base times height. But in this case, we want to write it in terms of B. We do not want to write it in terms of C. It needs to be written in terms of the base. Okay, so in that case, the base is a diagonal. So I'm going to use the Pythagorean theorem pretty much for any time you have a triangle and you don't have the base or the height, you can use the Pythagorean theorem to figure it out. So in using the Pythagorean theorem, because these are right triangles, it's a square, it has right angles in each corner. So b squared is equal to c squared plus c squared. So b squared equals 2c squared divided by 2. You get c squared equals b squared over 2, and that's what we're trying to find here is c squared. So the area is equal to b squared over 2. So we have the equation of one cross section. Now we're going to use an integral to represent adding up all of the cross sections. So the volume of one cross section is the area times the thickness. Now in this case, because we're perpendicular to the y-axis, the thickness is dy. Okay, so that tells me that my equation and my bounds need to be in terms of y. Now, because we were given the equations in terms of x, we're going to have to solve for the equation in terms of y, meaning you need to have an x equals equation. So let's start doing that. So I'm going to start with the semicircle here. So I'm just going to color code it a little bit. So I have y equals the square root of 1 minus x squared. Square both sides, you get y squared equals 1 minus x squared. Subtract 1, negative x squared. Divide by negative 1. So you get negative 1 divided by negative 1 is positive 1 minus y squared equals x squared. And take the square root. Now, when you take the square root, what do you have to do? Plus or minus. So x equals plus or minus the square root of 1 minus y squared. Now, why is that? Well, the positive side of the square root is going to be this piece right here, because that's where you have positive x values, right? And then on this side over here, that's where you have a negative x values. So I should write that. Negative x values, like if you just think about a coordinate plane, that's where your negative x values are. Here's where your positive x values are. So when we're talking about our base, like right here, the base of one of those, or the diagonals of one of those squares, that is going to be the area between quote unquote upper minus quote unquote lower functions, or the one that's more to the right minus the one that's more to the left. So in this case, the base is going to be the positive square root of 1 minus x squared, and then the lower function is the negative square root of 1 minus x squared. Now that's different than over here, where the base is in between the line x equals 1 and the line y equals negative 1 over 2x minus 1/2. So let's go ahead and solve for this line here in terms of y. So we have y equals negative 1/2 x minus 1/2. So add 1/2 to both sides, y plus 1/2 equals negative 1/2 x. And multiply by negative 2, and multiply by negative 2, and I get x equals negative 2y minus 1. Okay, so that's the equation of the line in terms of y. So if my base is here, that's going to be between my upper, quote unquote, upper function, which is x equals 1, and my lower function, which is negative 2y minus 1. So that means I'm going to need two different integrals for this one, because depending on where your base is, it's either in between these two lines or it's in between these two square root functions. So let's go ahead and start setting that up. So I'm just going to set it up over here. So looking at the area in between, so I'm looking at this area down here. So that's in between the y value of the point of intersection. And the y value of the point of intersection, if you just set them equal to each other, you can solve. So if you plug in 1 here, 1 equals negative 2y minus 1. Add 1 to both sides, so you get 2 equals negative 2y. Or if you have a really accurate graph, which I don't have here, my computer will just not stop, you get y equals negative 1. And then it's clear from the graph that that ends at y equals 0. So this integral is going to go from negative 1 to 0. And we're adding up b squared over 2 dy. So that's going to be, I'm just going to factor out the over 2 part. So 1/2 b squared. The b is quote unquote upper minus quote unquote lower. So negative 2y minus 1. So that's the base squared dy. And then we also have, oh my gosh. We also have these upper bases here, those upper diagonals, which is the integral from 0 to the upper y value, which is 1, of the quote-unquote upper function, which is the positive part of this, so the positive square root, minus the lower, quote-unquote lower function, which is the negative square root part. So that's a positive minus a negative. I'm running out of room here. And that's the base squared over 2. So I'm just going to factor to 1/2 here. So base squared over 2 and then dy. Okay, I'm going to clean this up just a little bit more, even though I'm totally out of room here. So that's the integral from -1 to 0 of, I'm going to pull out the 1/2. And then 1 minus -2y minus 1, that's 1 plus 1. So that's 2 plus 2y squared dy plus 1/2 the integral from 0 to 1 of, and then because this was upper minus a negative lower, that obviously just becomes a positive. So that's the square root of 1 minus y squared plus the square root of 1 minus y squared, which is 2 square root of 1 minus y squared dy. Now in this case, you could distribute the squared part here, and get 4 times just 1 minus y squared, and the square roots would go away. But I'm just going to go ahead and leave my answer like this. So yeah, that is area of cross sections. Again, follow these steps. You'll get in the habit of it. It takes a while to get used to, just like anything else. And just remember that the idea of cross sections is you have a solid shape, and every single slice, like as in a loaf of bread, every slice of that shape is a particular shape, like squares or circles or whatever. Okay? All right, good luck.